Okay, so welcome to office hours. So just first a little bit of setup. So in online meetings on Canvas. Oh, this one's slow. Let me switch internet at my house. I don't know why. Sometimes one internet's really slow and another one isn't. So, I don't know why. I'm already doing office hours and it gave me a link for it. So, okay, so that's how you would join office hours. Link right here. Hit start. I think it's already started. I don't know why it said start. Or it didn't know I'm already in office hours. A little weird, but okay. Okay, so I'm gonna have each week we'll have that. And because the office hours, I'll often be addressing questions from a specific homework set. I will add the name of the homework set here. So let's jump into the homework that we're going to be talking about. So it's going to be homework 1. And this is the way the homework is going to go in general. We take a second to find homework 1. Homework 0 is due here, and then here's homework 1. And then here's the page. Your Canvas probably looks a little different, and then we want to download it. So I'm gonna take a look at some of homework 1 together. Hi, Naomi.
Hello.
How you doing today?
Good. Were you able to fix your AC?
Well, I got somebody fixing it now. It was a faulty capacitor, which I sort of know what that means, but
Yeah, it's hot out here too.
yeah. So where are you?
I'm in Charlottesville.
Okay. Yeah, me too. It was hot. It was hot here. So I found okay, nobody needs to know about my AC, but I took a box fan and put it on top of the outside AC unit and turned that on, and that kept the house reasonably cool because the fan wasn't running out there. Um, and when the AC person came to fix it, they were like, I was so embarrassed. I was like, I just stuck a box fan on there. I'm probably an idiot. This is probably, and they were like, that was so smart. You kept your house cool by doing that. Are you an engineer or something? So anyway.
Cool.
Um, okay, so
Oh, I'm the
um,
only one?
yeah, I think you're the only one with this. I think Dima tried to join, but I didn't have the link because I up and didn't get an announcement out because I was delayed. So
Yeah, I kept
yeah.
watching that communication, and then maybe I can post this to the teams.
Sure, yeah.
If I can find the
Okay. And I think I posted it to Teams as well, but if you have a spot to post it to or you want to, I mean,
Oh, you
that's all good.
posted already?
Yeah. And I tagged Dima in it. But if you want to post it at all as well, yeah, please do. Oh, you can put the link in there. Good job. Thanks.
Yeah, I hope that works.
Okay, so I'm going to share my screen. Okay, so what I did, I went into, I started recording, and I might apologize for anybody who joined if I wasn't sharing my screen earlier and I was talking just a moment ago, like I was sharing it. So if you go to modules, so to find homework 1, I mean, everybody probably knows how to do this already. And it's going to be in module 2, and you scroll down, And then here's the homework 1 assignment.
Yeah.
So if you click on there, you can download it. And then I have it open as a PDF. Okay. So I'm going to walk through a little bit of this. And let's see. Trying to figure out the best way. Oh, I know what I could do. I want to make it bigger and I want to be able to write on it. So what I'm going to do is take a screenshot of this and, oh, even better, I'm not going to use PowerPoint. I'm going to do something else. Here we go. We're going to be cool. So I'm going to use my whiteboard app, which is really good when it works. It always seems weird to me that the whiteboard app takes a while to load up because oh, I'm on the slow. I didn't switch over to my. Or I won't pause, but you'll see me freeze. Okay. There we go. So I'm going to get a new whiteboard. And start with a blank canvas. Okay, I found one that I really liked the setup. And we're going to use this. So take a moment and erase everything here. Maybe. Can I select it all? Okay, we'll just start in a new spot down here. Okay, so here's the homework. And let's start by taking a look. So the first step is to really just be able to read what this is saying. And so let me get my red pen. So you are a data scientist, right? So I'm reading starting from here. And you're choosing between 3 approaches to solve a data science problem. And so our approaches are approach A, approach B, and approach C. And so if you try approach A, then you spend a total of 4 days. And here, I'm going to pause. I'm going to pause for just a second. I'll be right back. I'm just going to stop. Are we resume recording? Okay. Okay, so we're a data scientist. We've got three different possibilities to solve a problem, right? And I don't know, just I won't even make up a story. Right? The three different approaches: approach A, approach B, and approach C. But we have no idea which one's gonna work. So with approach A, we would spend 4 days coding and running the algorithm, but it will not produce any useful results. With approach B, you'll spend a total of 3 days. So I guess this is the important part, 3 days coding, and it will not produce useful results. And 4 days, and I'll underline the same kind of statement for A. But for C, you'll spend 1 day coding and running the algorithm, and it will give you the results you're looking for. So you're starting your project and you do not know which approach is going to work. So you're equally likely to choose among the unselected options. So we're just going to try the different approaches, and each time we try to pick the next approach to use, we'll just pick randomly out of what's left. So you're equally likely to choose among the unselected options. So I'm up to here. But if your selected approach does not work, you'll select a new one and continue until you get useful results. What is the expected time in days? So we're asked for things. So I always like to highlight, maybe even get a different color, but what are we trying to solve? Right. The expected time till we get a results, and what is the variance on that time? So those are the two things that we should be answering. Hi, Wyatt. Good afternoon.
Hello.
Happy Friday.
Yeah, happy Friday. Hope your AC's back on because it's a hot one.
Thanks. It is back on, and yeah, a nice woman came and fixed it, so it was good. Okay, so here's a couple of ways you can think about this, and this is one of the things in the Bayesian machine learning. It takes a little effort to take a verbal description of a situation and turn it into math that we can use, maybe Bayes' theorem or just probabilities on. And once you do that set up and you understand what it's asking for, this problem's not going to be real hard. But let's I'll kind of draw a diagram. It's not really so much of a standard way to draw a diagram or anything like official. Oh, and why we're starting on homework 1, and we're going to walk through problem 1. And after we walk through this, I'll give a reminder of kind of the structure of office hours. But office hours, I'll usually start by walking through some of the homework. Okay, when we start, we might take option A. We might take option B. We might take option C. And so from the problem description, if we take option A, is that going to work or not work?
No, it will not.
Yeah, it will not work. So we're going to get to some point, and then we're going to have to pick between the remaining options, which will be B and C. What about if we take option B at this point?
No.
Also, no.
Also no. And then we'll be taking either A or C. And what about if we take C?
Yes.
Yeah, that works. So that makes us happy. So we get lots of hearts. So maybe I'll put a check mark there to say yay. Okay, if we take A, how many days does A take?
1.
Let's go up here.
I think 4.
A takes 4 days.
Oh,
So
yeah, sure.
I'm gonna try to just draw that somewhere on here. There's no like right or wrong place to draw, as long as we get something that helps us think through this. And then B, each time we use B, how long does that take?
3.
3 days. So expand this a little bit. When we take 3, B takes 3 days. And what about C?
1.
1 day, right? It says right there. Okay, so this, we now have all the stuff off the homework that we need. Okay, so this is our diagram. So when we start, we have like 3 options, and it's all equally likely. So we have, and I don't know, I could draw a little box around each of these probabilities, but, or I know what I'm gonna do. Let me grab a different color to help distinguish this a little bit. Okay, so I'm gonna take green. Green will be what I'll use for probabilities. So there's a 1/3 probability that we're gonna take this route, a 1/3 probability we're gonna take this route, and a 1/3 probability we're gonna take the bottom route. Okay, so if we take the top route, which is this one, we get here, then we have to try again because we didn't get the right answer when we've got 2 options. So what are the probabilities for each of those? So if I'm right here and I'm deciding I might take B, I might take C, but I don't know which one's going to work, but they're equally probable. What are the probabilities for each of those options?
1/2.
Yeah, 1/2. So 1/2 probability, I'm going to take this one. And then that's supposed to be a 1/2 that I take this. Same thing here. I've got a 1/2 that I'll take this one, and a 1/2 that I'll take that one. Oh, and I didn't follow this out all the way, right? If I take A here and then B here, and I get to this point, have I finished?
No, you would still take C.
Yeah, so at that point, I need to take C, right? And then it'll be done. If I took A and then C, and I got here, I'd be done. See if I've got a nice. Check mark. Okay, I'm clearly not competent at using this. Can I drag? Why can't I drag the? Okay. I'll stick to drawing. So I've got red. So here, if I take B and then C, I'm done. But like we talked about here, I take B, then I take A, then after that, I have to take C, and then I'm done. So anytime I have to keep going till I get C, even though I don't really know that. So at this point, that would be done. I can get here and that would be done. Get here and now, a check mark means I'm going to stop. So we're really drawing out a tree diagram, and trees tend to be really useful ways to keep track of things. So kind of that's the one principle that we see here is trees are nice ways to keep track of things. At this point here, it's kind of obvious, but after I've done B and A, right, where I just put this number 1, I only have one choice from, and I have to pick C. Same thing up on the top route. If I start with A, and then I try B, I only have one option at this step. So I'll put a 1 for probability 1 there. And I almost don't need to put it in, but it's going to, for completeness, help us out a little bit. Okay. So I'm going to go for light blue now. What's the probability that I take this route to get to the solution? And the answer is, you might be able to get it, but I'll give you kind of a hint of where we're going. If I say, what's the probability I'm going to roll a 6 and then flip a heads? you would, and we did this, kind of talked about this in class a little bit, you would say, oh, the probability of rolling a 6 is 1/6, probability of getting a heads is 1/2, so it's 1/6 times 1/2. This route that I just did in blue has an event that'll happen 1/3 of the time, and then the second one will happen 1/2 of the time. So the probability we follow this route is 1/3 times 1/2 times 1 equals 1/6. So the probability that I take this route is going to be 1/6. And the if I take that route, the one that I have highlighted in blue, how many days would it take me, would I have to work?
8.
I guess I didn't write them in. Hold on. So I've taken the 4 here. B we said takes 3 days, and C takes 1 day. So you add those all up, and we get 8 days. So A is always 4. C is always 1. Okay, so taking this route that I have in blue, I have the probability I take that route is 1/6. I'll call it N, the number of days is 8. Okay, now what you need to do, so these are the two important pieces of information for this route. You need to look at all the different routes, and you need to look at, for each route, the probability of taking that you wind up taking the route and the number of days it takes for that route. And the they are asking us for expected time. And so that's the expected value for the number of days. And then the variance in this time, which is the variance for the number of days. So we look for our formula for an expected value. The expected value of X, that's equal to the sum over all Xi of the probability of Xi times Xi. Right, so that's our key formula here. Now, when you have a couple of possible outcomes, but they're all equally likely, then this probability would be, hi, Dima. Sorry, I didn't have a link early.
Hi, Professor. Yeah, I'm here. Thank you.
Okay. So expected value here, it's the probability of each Xi times that Xi. In this case, Xi is a different number. So if I have like, let's say if I'm going to play the lottery and I have two possible outcomes, X0 is $0 and X1 is like, if I win, it's going to be like, say, $1,000. And probability that I'm going to lose is 0.00001. Maybe I took too many zeros, or I did these backwards. So it's the P of X1 is the probability of winning. P of X0 would be, actually, let me write these better. So I want to know what's the probability I lose and what's the probability I win. And the probability of getting X0, that's losing, that's say 9999 over 10,000. So most of the time I'm going to lose. But the probability of winning, like 1 out of every 10,000 times, I'm going to win. So the expected value or the expected winnings if I were to gamble or play this lottery game or whatever it is. So the expected value of X, where X is my winnings, it would be 0 times, right? The 0 times the probability of getting 0, 9,999 over 10,000 plus, and then we got to go through the other case, which is 1,000 times 1 over 10,000, right? And so do the math. This piece is 0. This is 1,000 over 10,000, which is 1/10, which is right 0.10 dollars. So my expected value would be to win 10 cents. So if this was some game where I might win $1,000 or I might lose my whatever it costs to play the game, then I would look at the expected value of the different outcomes, and then I could say, okay, my expected value of winning is 10 cents. So if it costs me more than 10 cents to play the game, I probably won't play it because I'm probably going to lose money. But if it costs less than 10 cents, I might play the game. Of course, if it costs 25 cents to play the game, which would probably kind of be reasonable, like a raffle at a fair or something, I might be like, I don't really care if I lose 25 cents and this sounds like fine. So, but I just, as a total aside, that's completely unrelated, I tend to not gamble. I had a friend who used to say gambling is a tax on people who are bad at math, which is kind of true, I think. But okay, so back to our problem in the homework. So we've got a bunch of different routes to get to the final solution. Each route has a probability that we take that route. Each route has a number of days that it'll take that route. And what you need to do is do the expected value, in this case, expected value for n, and it'll be the probability overall ni, maybe ni is like the route, and then times the number of days. So x here would be n. So that'll give you the expected value, right? And you would do that for that route, and for this route, and for that route, and for this route, and for that route. So that'll give you the expected value. And then the variance for x is the sum overall xi of xi minus the expected value for xi. Maybe I'll put this in parentheses squared times the probability of xi. Now, this should be familiar to our sort of more standard or more basic version of variance, right? The variance in a standard case is usually sum 1 over n times the sum of I times xi minus mu squared, right? So the 1 over n corresponds to the probability in this case, in this top here that I wrote, like this, the basic version. That's when you have a couple of possible outcomes, but they all have the same probability. But in this case, the one we're doing with this tree problem, not all of those routes to get to the solution have the same probability. So that's why we can't use just this standard thing, why we have to use this one here. Okay, so any questions on that? I didn't give the answers, but I gave the two formulas here that you need to use, that one and this one. And this picture here explains how to take these different options and compute what you need. But any thoughts, questions?
This is helpful. Thank you.
Okay, good, good. That's good to know. And this is the way I'll often do on office hours. I'll help you to set up and frame the problem. Maybe I'll give you for on the homework problem, and maybe I'll give you the formulas you're supposed to use. Maybe I'll walk through, like we have in this case 5 different possible things, possible routes, and I'll walk through one of them and like do some of the computation for one, but I'll leave it to you to do the others and put those in the formulas. Yeah. Okay, good. So let's go back to the homework, and I'm going to grab 2 and we'll go back to our whiteboard, and I'll place homework 2 here. Okay, suppose if it is sunny or not in Charlottesville, depends on the weather on the last 3 days. So what I'm going to explain in this setup, I'll explain to what the problem's asking, but it uses something that we haven't talked about yet. So I'll just I'll explain what it's asking, but then we'll leave it at that. Okay, so the sunny or not in Charlottesville depends on the weather the past 3 days. And to show this how this can be modeled as a Markov chain. So we haven't talked about Markov chains. So this part won't make any sense unless you've seen them somewhere else or maybe read ahead or something. By displaying a diagram and a transition matrix. So a little thing, when we get to Markov chains, a little thing to make sure you pay attention to is what's the diagram for Markov chain and what's the transition matrix. But this is what it's asking for. We have 2 possible days, 2 possible weather categories: sunny, or I'm going to pick the alternative as rainy. But I mean, it could be sunny. Maybe I should call it sunny or not sunny. But suppose it's sunny or rainy, and I could say the sunny or not depends on the weather of the past 3 days. So if I write out the past 3 days being sunny, 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 then I have today's weather. And for today's weather, what I want to do is give you a probability that it's going to be sunny, given that the past 3 days was sunny, sunny, sunny. Right? That's the type of thing that we want to do. We could also say, I want to get the probability that it's going to be rainy based on the data that it was sunny, sunny for the past 3 days. Of course, because I only have 2 options here, that one is equal to 1 minus the probability that it's sunny based on sunny, sunny, sunny. So I don't really need to think about this. If I get this one, because I could stick it in there, that would give me everything I need. So what you'll wind up wanting to do is get the probability that it's sunny, given the past 3 days were sunny, 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 probability that it was sunny, given that the past days were maybe sunny, rainy, sunny, probability that it's going to be sunny, given that the past days were rainy, rainy, sunny, and then like so on. And so that's going to be the goal, but we haven't talked about how to do that. But something that's going to help us do that is this idea of a diagram and a transition matrix. And just one more thing to clarify. This is show how this can be modeled as a Markov chain. You're not actually going to have to compute all of these probabilities. You're just going to be able to show that there's something you could compute based on using a Markov chain, right? But this will make more sense when we get to it. Does that kind of make sense? Just we're predicting the weather each day based on the past 3 days?
Yes.
Yeah, okay. And let's see if there's let me just mention the ones that we're not going to talk about today. Number 4, we're not going to talk about today. We'll talk about that office hours next week. And 5, we'll do office hours next week. And if we need to get those a little sooner, 4, 5, and 6, then we will. Like if I need to do an office hour, like a kind of just a supplemental help walk through for those. I have to double check how the timing is, right? So usually I like to have it so you have some time to think about it, but there's a good chance you won't. I mean, you might get the answer, and that'd be terrific. But you'll probably get some kind of answer sketched out, but you might not be sure if it's really what the question's asking for or whatever. And then you'll come to office hours, and office hours I'll give more details, and that will fill in anything you weren't sure about usually. And the first office hour will be where I kind of like what we're doing today, where I help you set it up. I show what things you have to look at, but I leave a bunch of work for you to do. If you look at that and you're like, hey, I did this piece, and I'm going to ask you another question. If you ask me questions on Teams or whatever, then I'll give you more complete things. Right, so
To look at the questions for later, where can we get the data set? Like
oh, that's a great question. Okay, yeah, maybe I'll take the time to walk through this. This one, number 3, we walked through in class, so I guess it's really not it's not worth doing this one. And I'll just do like a really high level view of it, of what the idea is. So we get a bunch of observations, and the general idea is if I don't have much data, then I have a pretty broad uncertainty, right? If I go fishing for one day and I catch one fish, I don't know that every day I go fishing, I'll catch one fish. Maybe only half the time I catch a fish. Maybe 80% of the time I catch no fish. Maybe I caught one fish today, but other days I go fishing, I'll catch 8 fish. Because I don't know, the one day I went, whatever, right? If I have one data point, I don't know, a big deviation. If I have 5 data points, I would have something, this probability distribution is like on maybe how many fish I would catch or whatever, right? And so I might have a like less uncertainty. So it would be something like this. And if I collect a huge amount of data, then, right, my normal distribution for what I think the number of fish I would catch, or the actual mean height of flowers in my yard, or whatever it is, this would be what we get. So this is what we get if we have a lot of data, and this is the situation with little data. Yeah, so by getting more data, you can decrease your uncertainty, and you have to read through all the pieces of this and where the formulas are. But the question is, how large of a random sample, which means what's the minimum value for n, or how many data points do you need to, and the second part is to get the spread on my standard distribution down so that 95% of the data is between mu plus 0.5 and mu minus 0.5. So I know how much spread. I'm going to be 95% confident that I'm within 0.5 of my mean. And so how many data points do I need to decrease that uncertainty down to that point? Okay, so let's go and look at those other two. Yeah, and I definitely should help you get started on these, which we can certainly do. At least you can kind of start playing around with it. Okay, you started an online business selling books. So reading from here on number 4, that are interest to your customers. Publisher has just given you a large book with famous 20th century photographers. You think this book will appeal to people who have bought other art books. So this is common. It's like a recommendation system. What if somebody's bought history books before? Will this new book of 20th century photographers be of interest to them? If they've bought coffee table books, maybe this is a bit of a coffee table book. It's kind of like that category. Maybe those people would be likely to buy this. So the the goal is to figure out what's the probability somebody's going to buy this new book based on their previous purchase history. And that would help you efficiently target customers, or if we want to think about increasing your sales, like who do you want to advertise to or predict how many people are going to buy it, or also not waste the time of people who aren't going to buy it, right? They don't want junk mail. You don't want to waste money sending junk mail to people who aren't going to buy it. So that's the kind of the goal. And they say, look at this art history books.csv. And so if you want to use this, go to the files here, and there's art history books. So we want to download that. And that's downloaded there. And I like to use VS Code. So let me open up VS Code, and I'm going to go and I'm going to make a new folder in Python, and I'll just call it temporary, because I'm gonna make a folder and put a little code in here so that we can take a look at this CSV file, right? So I've made that file, and now I want to go to my downloads. Art history books, and I want to cut documents, Python temp, and I'm going to paste it in there. So now that file is in there. And now I'm going to go into, I like VS Code, and I'm going to say, make a new file. So I see art history books is in this folder. I'm going to make a Jupyter notebook. And I know I'm going to want pandas. So I hit run. It's going to say, hey, you haven't picked a kernel. Okay. Or you haven't picked a Python environment. The one I like to use for me is 3.11. So I hit run, and then it runs. I'm going to give myself a new block, and I forget offhand how to read a CSV file in pandas. So I'll copy that. Nice thing about Python, if you're ever not really sure how to do something, oops, it's not going to be called data.csv. It's going to be called art history books.csv. And so here's the data frame, right? Or maybe if I like to, a couple of different ways to display it, I can just write df, and that makes, I think that's a little bit prettier. You can modify how many columns or rows you display. But okay, so what this is, each row is a customer. This is customer 0. This customer's past history is they never bought an art book. They never bought a history book. They bought one table book, and they did not purchase the new book that we're offering. So I could look at, let's go here, we'll go into Python and say Python Panda. Suppose I want to know how many subset data frame by condition, right? Suppose I want to know how many people bought the new book, just as a information. So maybe I want to subset this data frame. So here's my data frame. So I'm going to say result data frame is the data frame where the data frame of purchase equals 1. So that'll get me a new data frame called result data frame, and I can display that. I can display it here. And so you'll notice everybody in the purchase column has a 1. And just by looking at the number of rows, I know I have 89 people that bought this new book. Turns out maybe I don't want it to equal 1. Maybe some people bought more than 1 copy. So maybe I want to say more than 1. Oh, I guess nobody bought more than 1. Okay. All right, so 0. So, but maybe I want to say, maybe I want to look at just people that bought the art book. And you'll notice some people bought 2 different art books. I guess the assumption here is that there's different types of art books, and somebody might have bought a art book on Monet and another art book on watercolors or whatever, paint by numbers. And so there's 2 different art books. There's lots of different art books, so maybe they bought more than. So here we're going to look at the number of people. So 301 people bought at least 1 art book. So this is all the people that bought an art book. So now, suppose I want to say out of these people, suppose I want to say art new. I want to say people that bought an art book and the new book. I might say well, a couple of different ways I could do this. I could take the people that bought at least 1 art book, and I could say subset that and take all the people from that category that purchased this new book. And I've got this. So, it printed it all because it wasn't that big. And I don't really need to see all of it. I just want to know how many like how many rows there are here. And is there just rows? Sorry for me guessing. Okay, so I don't know if you noticed, but in some of what I kind of guessed at, it showed what I want. But I want a nice way to tell me how many rows there are. How many rows in a data frame? Okay, so there's 2 ways to do that. I can do length of the data frame, or I can do the data frame in dot shape 0. So let's use the dot shape because I kind of like doing dot shape. So just like if this was a NumPy array, you can do dot shape. So that says this data frame that I have is 58 rows and 4 columns. So what does that tell me? That tells me, for example, print probability that I buy the new book, given that I've purchased at least 1 art book, equals this. And it's going to be, there were 300 people that purchased the art book. So we subset all our data to 301. And then out of those 301, we know 58 of those purchased a new book. So, right. So that's going to be the type of thing that we're looking for in this homework. So I guess I kind of got you partway started. So you can think about the problem, and you're going to be trying to look at conditional probabilities like this. Like, given that I purchased what's the probability I'm going to buy the new book given that I've purchased an art book? Right. So if I just wanted to do, what's the probability I buy the new book if I don't know anything about my previous purchases? How would I do that?
I guess you're assuming a uniform distribution.
Yeah, so I'm assuming no priors. So if I or a uniform distribution, everybody has the initial the same probability of being in the categories. So just probability to buy a new book. Right. So let's just think about that for a second. If I say, hey, what's the probability that somebody comes in my store is going to buy a can of soda? How would you tell me how to do that? Assuming history, right? If I know everybody who came in the store and I know whether they bought a can of soda, how would I do that?
It's the probability of buying a soda given their previous purchase history.
Yeah, I'm asking an even simpler question. So if I want to know how many people, what's the probability somebody bought a can of soda, I would just look at how many people have come in the store and how many people of those bought a soda, and it would just be the number of soda buyers divided by the total number of customers. Right. So so here's what I want to do. The number of all is data frame dot shape 0. So this is a number of all of the people that I had, which is going to be 1,000, right? Because there's 1,000 people in this database. Now, the number of people that buy the new book, and I haven't made a database, have I, of just people who bought the new book. So I have this one for art. So I'm going to repeat this, but for the new book. So this will tell me, this will make a database or a data frame, and it's going to be the data frame of all people who bought the new book. So we have 89 people that bought the new book. So come down here, and the number of people that bought the new book is going to be this. It's going to be shape 0, or the number of rows in that data frame. The number of all people is going to be that. So if somebody just said, hey, if I ignore their purchase history, what would be their probability just out of all the customers that somebody's going to buy the new book? So it would be this, buy new. Right. And so, well, I'll hit print, and then we'll talk about, clarify a little bit of what my things are going on inside of this print statement. Okay, so what did it not like? Unterminated literal string. Oops. Okay, so I just had too many quotes. Okay, so this says the probability I'm going to buy a new book, which is this, it's equal to 89, and that's what I get when I put these curly braces around a variable. It just gives me, it prints the value of that variable. So it's 89 divided by the number of all the book, that's going to be 1,000, and then I do that division and I get 0.089. Or maybe maybe it's a little easier if I do. No, I think that's okay. Okay. So out of just all the customers, about 9% of them, or 0.089 of them, will buy the new book, or 0.089 is the probability they're going to buy the new book. If somebody's previously bought an art book, this is the probability that they're going to buy the new book, which is 0.192. So we could answer things like, okay, here's a pretty basic question. Are people more likely to buy the new book if I know that they've already bought an art book?
I would say yes, but
Yeah.
maybe I'm reading
Okay.
a bit too much into it, but does it matter the combination of books? Like they bought an art book, didn't buy a history book, but bought a table book.
Yeah,
Or
okay, yeah, and that's the kind of thinking you have to get into to answer the questions in the problem, to kind of think about what they're going to ask you.
I see, okay.
Yeah. But if we just think about art book information from them buying an art book alone, it's about a probability of say 0.2, roughly, that they're going to buy the new book. If they haven't, it's about a probability of like 0.9 that they would buy the new book. So it's about, they're twice as probable to buy the new book if I know that they bought an art book. And so that would be that's really helpful for making decisions on advertising or predicting how many of these we're going to sell, that kind of a thing. Okay, and so that's what the problem is going to ask you to do a bunch of predictions like this. And just for to clarify, it says use Bayesian analysis to give posterior probabilities. It's really, right, it's just getting probabilities, whether somebody's going to buy a book or not. And I don't know, I'll let you think a little bit think through the wording. Because we really want, what we did here is a little bit of a simpler problem. Well, okay, well, I don't want to get into it too much. But then let's take a look at this last one. The dataset CHD-data.csv contains cases of coronary heart disease, CHD, and variables associated with a patient's condition, systolic blood pressure, and then it gives us information. Just seeing this in the beginning, this is a kind of a standard problem where we want to predict whether somebody's going to have heart disease or not based on a bunch of factors. It's really not that we can expect to accurately figure whether their heart disease. We really care more. Are they a high-risk person for having a heart disease, right? Are they a high-risk patient? So maybe we only want to test the high-risk patients. If we test everybody, we waste a lot of money. And this is a really interesting thing in the medical field. If you test everybody, you waste people's money and time, so that's bad. But sometimes you'll wind up testing people, but they don't really have the disease, or maybe even if they have it, because they don't have these factors that make them a high risk patient, it's not gonna be a danger to them. So you wind up finding out that they have the disease, but you would be better off not even bothering caring, because maybe, so I'll give you a specific example. So prostate cancer in men, right? Most men at some point in their life will get prostate cancer. Most men, it doesn't really matter, and they die of something else before that cancer because it's super slow growing. So they only test it for people with some conditions, right? So if you found prostate cancer for somebody and they were 70, and the only thing you could decide to do, you could ignore it, which would be the same thing as if you didn't test for it, or you could try to take some aggressive treatment for it. But that aggressive treatment is going to be more harmful than the prostate cancer would be if they're not a high-risk person. So doing this sort of, and that description I just described, it's really interesting. That's a Bayesian analysis type situation. Like, what's the expected value for the best outcome based on a bunch of different decisions, right? Okay, so back to this. I think I'm going to leave it for you to read and think about this a little bit. The place to get that data is the same place that we had before. So files. And by the way, I probably ramble a little bit in office hours. So feel free to like watch it at double speed and then hit pause and come back when, you know, you hit a point you care about a lot. So what was it? With CHD something. So it's this here. We want to download it. And okay, there it is in my downloads. So let me go over my folder. And I'm gonna copy and then documents. But I think I put it in Python and then temp. So I'll paste it here where I had the art history books. So now I can go back into VS Code. And so here's my two things. Oh, I have this untitled notebook, and let me do save as. And the first one, maybe I'll save this as bookstore.notebook. And I'll make a new notebook file. New file, Python notebook. And I know I'm going to want to import pandas, so let me go ahead and just grab that from my other notebook and run it. And then I'm going to want to read in the CSV file as into a data frame, and this CSV file CHD data. And then I'm going to display that data frame. Okay, so it's pretty good. Here's our data frame. We have systolic blood pressure, whether they use tobacco, cholesterol, adiposity, family history for coronary heart disease, whether they're type A personality, whether they're obesity, how much alcohol they use, their age, and then the last column is whether they have coronary heart disease. So you're going to do work similar to what we were looking at before to be able to say, what's the probability of having coronary heart disease based on these other factors? And maybe more importantly, which factors are the biggest contributors to having coronary heart disease? So which were the ones, you know, that really matter? If we were doing a machine learning problem, we might say, okay, just assume all of these and take them all and give me the best algorithm to do prediction of coronary heart disease. And I don't know, maybe it's a random forest or whatever. But in the Bayesian world, we care a lot about which factors are really the ones that are doing the contributing and how do we understand that, and not just make a prediction that's as accurate as possible, but predict probabilities of getting coronary heart disease. So that's going to be the perspective of the problem. But I'm going to leave. I think this is about as much. We've got the setup. You can look at the data, and I'll leave it to you to think about the data and think about how to do some computations from there. How's that sound?
Cool. Yeah, that sounds good.
Okay, good. Do either of you have questions for today, other than, you know, the homework one, or really anything?
I had a question about the project.
Sure.
I'm wondering about all the examples I had proposed to you involved temporal or time series data, and that's not something we've tackled in the program yet. So I didn't know if there were some maybe like external resources that you could point us to learn about regression models with time series.
Yeah, I will tell you sort of my favorite regression model with time series example. And let's see, it uses something called a Gaussian process. And I forget, did I mention the Gaussian process in a response to you, or have I not gotten to yours yet?
Not yet. Well, you didn't mention specifically, but I did read a bit about it in the example you had shared from the predicting food insecurity that you had done with your doctoral student.
Okay, yeah. So looks like Kaggle's getting slow. Sometimes Kaggle is slow while I'm doing a Zoom meeting, but that's okay. It's still working as long as it works. So I have a notebook in here on predicting gold prices, and it's going to be predicting future gold prices based on time series for the previous gold prices. So I want to predict the next 20 days worth of gold prices based on the previous 80 days of gold prices. So I'll throw this in the chat in case that's helpful. I think the recording has a keeps track of the chat. And oh, so this is the gold prices data that I put up. So is this, oh no, I apologize. Here's the one I wanted. Predicting gold prices. So, I mean, certainly feel free to look at those other notebooks. There's probably lots in those that I put in. And that was just somebody else's predicting gold prices problem. So notebook. Okay, so looks like this notebook had there's a bug in it. So this uses something called the Gaussian process, which is a Bayesian method. And I don't have a short description of it. Certainly, if you look up Gaussian process, it's really, there's some good articles, and I think this one here, this distill.pub, we're going to use when we understand it. So it's a good thing to get into. And one way to think about what a Gaussian process is, you're predicting a vector. Your output is a vector of values, not just a single value. So it's like doing regression, but you don't have just a one value in your regression. You have like a series of values, but there's conditional probabilities among the things that are in the prediction. Wow, it's so slow today. Okay. So, right, so this is our time series data. It's the gold price over a series of 1,300 days. Doesn't really matter that it's the price of gold. It's some value over a time series. And when you train the model, you tell it, here was 80 days worth of data, and then here's the next 20 days to make a block of 100 days. So your input is this X and your output's the Y. But it's not just like a vector of length 80 and then a vector of length 20. It's all from each day, you have a conditional probability on the next day. And if you think about in terms of like the Markov chain, problem that we haven't got into, but it's like, given the past 3 days of weather, how do we predict the next day? What's the probability of the next day? And so here's an example of the type of prediction. So if this is your previous gold values, your time series data for the previous, then over here, the predicted is going to be the red, and then the blue is going to be the actual. And what you can see is the prediction is pretty good for a while, but then after maybe 15 days or so, they start diverging. And then I put in some different methods, and let's see, is there anything else in the notebook? Okay. Yeah, so that's if I were going to do something with time series and it was a Bayesian class, I would do that. And there's lots of reasons for doing this because you get a sense of how quickly things are going to diverge from your prediction. So you get this prediction, but you also say, oh, it's plus or minus 5% for the first 10 days. But after that, the prediction starts getting wider. So it's a very Bayesian way to look at things. I don't know, is that something to point you in the right direction?
Yeah, I think so. That makes sense. I don't have to read into it. It reminds me of, I don't know, when you see like weather prediction data, and as the prediction is farther out, those kind of spaghetti charts start to get wider and wider.
Yep. Yeah, exactly. That's right. Yeah, those often weather prediction, economics, time series often use Bayesian methods so you can quantify how confident we are about the next few days, and then how long we can be confident in that. So, yep.
I'll let Naomi go, but I do just have a follow-up question.
Okay. Sounds good.
Yep. Thank you very much.
Okay. Thank you, Naomi.
Bye.
Oh, but by let Naomi go, I didn't mean
I
literally
mean,
let her go.
yeah, okay. Let her go if she had a question, but okay.
Sure.
That's fine.
So when you say your y value in this process is a vector of values, would that be, I mean, I'm thinking in terms of if we were predicting like the political instability of a certain country using, say, their import reliance for staple crops and their GDP per capita and things like that year to year. I guess I'm getting confused about where the predictor versus y values are going, and because in the gold prediction you're predicting based off of the previous value as opposed to predicting based off of a collection of predictor variables.
Yeah, so in this example, and okay, so this takes a random point, and then it takes a random stretch of 80 days for a time series, and then makes a prediction for the next 20 days and compares it to the actual 20 days. So in this example, I could, each time I run this block, it'll pick a different random set. And you can see here, it looks like my predictions are good for 12 days. Maybe I can take a few more. Now, that prediction was not good for 12 days, only good for like 4 days. Right. So what you can do, this red curve is the most probable prediction, but you can also show a bunch of other curves that would be like predictions that are within the 95% confidence interval. And so those might fluctuate up or down, and those would tell you what kind of instability you're going to have. So bringing it back to your problem, if you were predicting like political instability.
Yeah, just as an example, or if that was your response variable, and then your predictors were maybe just like like instances of civil unrest and like like an index score of government,
Mhm.
accountability, and like different predictors, and you're using multiple predictors to predict whatever your response variable is.
Yeah, so you could imagine, let's do not years, but like months, right? And I want to predict, you could think, oh, I want to predict political instability next year or for civil unrest next year. But let's make it like civil unrest over the next 12 months, right? And so, and there might be some regular cycles that are in that, which this method would handle that, because in the predictions, like this red prediction, if you creep up like these 4 days, this next little bit would be a likely next little bit. Like it similar to how natural language processing, you tell it the quick brown fox, and then it thinks jumped over the lazy dog. What it does is it predicts jumped as the next most likely word, and then over the next most likely word, and then lazy the next most likely word. Although it kind of does it all at once, but it's really that sequence in that order is the output, the Y value or things being predicted. So this sequence of values is a reasonable sequence. So if you were talking months, it would go up and down with any seasonal variation as part of that. But you would think of this side here, we have 80 days, or just think 12 months of civil unrest, but you'd also have 12 months of some economic value, like percent of people who are unemployed. You'd also have a previous 12 months of what other valuables, the amount of famine or something. And so it would combine all of those different inputs into the piece that's on this side, which would be your input, or what we often call X. And then the Y would still be this vector, but it would be based on all those.
I see. That makes a lot of sense.
Okay, good, because I wasn't quite sure I said it well. I got to the end, I was like, did I say that well? But I think I really just said it handles, yeah.
Cool. And then if you have time, I don't want to take a bunch of time, but I do have one other question.
Sure, go ahead.
In terms of those input variables that would go on the left-hand side here, is there some normalization process that needs to happen? For example, if it's like one of your inputs is percent of unemployment, but the other one is like famine occurrence, like those are on very different measurements.
So it turns out for this, you don't have to use a normalization process, because it really does all the normalizing for you. If you do a normalization process, then it might be like, what I would probably do is, if it was like famine that's in percent and GDP that's in dollars, I might rescale GDP by 3 decimal places so that when I plot them, they're not just so different that I can't visually just compare them, but there would be no aid to the algorithm. There's no reason for the algorithm to normalize them. It does the normalization.
I see. Okay. Awesome. Thank you.
Yeah. Okay, good. Yeah, you're welcome. Yeah, and once you get some code, one of the things with the project that I like is this, like you and I are just going back and forth here, shooting the breeze about ideas. And then yeah, I just kind of enjoy that part of the projects. So that's what I foresee. And then you can go get your data and test it out, and then you can come to me and say, my code is stuck here, or how do I make this prediction, or does this thing make sense, that kind of thing.
Cool. That sounds great. I'm
Yeah.
looking forward to it.
Okay, good. Yeah, me too. All right, take care, Wyatt.
You too. Have a good weekend. Bye.
Thanks. You too.